We have chapter 14, activity 2 today. And it's going to be talking about mainly epoxides. So how do we make them and what can we do with them? So epoxides are basically a special type of ether. Right? It's a 3-membered ring that contains an oxygen as one of the members of the ring. Because there's a lot of ring strain in a 3-membered ring, epoxides are very reactive, which is in contrast to normal ethers, right, which are anything other than that. So it could be an acyclic ether or even a cyclic ether as long as it's a larger than a 3-membered ring. So these are basically not very reactive. The exception is the epoxide because of the ring strain is very reactive. So that's why we spend a lot of time on epoxides because they have a lot of what we call synthetic utility. We can do things with them to make other things, whereas we can't really react ethers to do a lot of other, make a lot of other things. Okay, so we're going to be looking at 2 ways to make an epoxide, which this should be a review reaction for you. Should have been introduced last semester. We talked about addition reactions of alkenes, and it was the first step in a 2-step sequence. So if you recall, right, last semester you probably learned that you treat an alkene with MCPBA, you form the epoxide, then do a subsequent treatment with acid, and you get an anti-diol. We called it the anti-dihydroxylation. Okay, so that's where you've seen it before. And so basically it's just kind of like looking at what's going on in the first step, right? Without adding acid after, we can isolate the epoxide and then use it to do something else other than make a diol for adding acid. So we can just use MCPBA, what it looks like. Probably, I'm sure it's in the video, but we have metachloroperoxybenzoic acid, right? The aromatic ring and the chlorine don't really matter. It's this sort of RCO3H. Sometimes it's just written as R. This is a specific type of peroxybenzoic acid. It's used because the byproduct, metachlorobenzoic acid, is a solid in dichloromethane, so you can just filter it off. So it's very convenient. That's why the chlorine is there, because without it, you wouldn't have the nice solubility properties and being able to just filter off the. And it makes this a solid, which is easier to work with as a reagent. Solids are always easier than liquids. It's easier to measure out some powder and put it in a flask than deal with a liquid. So that's another advantage. Anywho, this transfers an oxygen, specifically this one, to an alkene to make an epoxide. And notice how they have both wedges up. They could have also drawn them both down. The enantiomer is produced as well. It's just a requirement of the 3-membered ring, right? If one is up, by definition, if you're going to have the other carbon attached to it, it also has to be pointed in the same direction. Okay, so another alternative set of reagents that you could use to make an epoxide are this 2-step sequence where we do a halohydrin reaction. So this one is also reviewed. Halohydrin from the alkene addition reaction chapter. Where you basically add a bromine and water, and OH, across the double bond, and then followed by sodium hydroxide. So when would it be an advantage to use this condition versus this one? So on small scale, you would use this one because it's much easier. It's only one step. But the problem is MCPBA is expensive. So on large scale, it's just not economical to use it. So then you would use more of this 2-step sequence with cheaper reagents. So, but they both do essentially the same exact reaction. There's just scale advantages to one or the other. So in the second one, right, we really didn't show the mechanism here for the halohydrin formation, and that's because it's a review. So you could go back to chapter 8 and you could review the halohydrin reaction. And but one thing to note is that the bromine and the OH do end up opposite. So anti is the stereoselectivity. Then if you treat this with sodium hydroxide, then we'll have a deprotonation. And there's not a significant pKa advantage to this proton transfer. You just have to add a lot of hydroxide. Or the driving force will be the next step, actually. So as soon as some of it's deprotonated, it immediately goes on to do the next step, which is irreversible. So that essentially makes the reaction go. So my point is that this is not a very strong base to deprotonate an alcohol, but it's okay. Okay, so we would do a proton transfer that forms this alkoxide. And then it's set up nicely because these are anti to do an SN2 reaction. So because this can attack from the top, right, the O with the negative charge is pointing up. It attacks from the top of this carbon, which is opposite the leaving group. So it's perfect to be able to do an SN2 reaction, right? Because essentially it's already pointed up, so you can attack from the back, kicking out the bromine, and then we get our oxide. And in a way, you can kind of think of this step, even though it just says SN2, it's also could be called a Williamson ether synthesis. Because remember, what's a Williamson ether synthesis? You start with an alcohol, you protonate the alcohol with a base, and then it does an SN2 reaction, right, to form an ether. And an epoxide is just a special type of ether. So it's really just a application of the Williamson ether synthesis to make specifically an epoxide, which is a specific type of ether. Now, it might seem weird that this is a tertiary carbon and we're doing SN2 on that, but it's possible in this case because it's an intramolecular reaction. So and the nucleophile is strong and it's right there. So it's probably more like SN1, SN2-like. So basically, this is probably already a weakened bond, right? And then the nucleophilic attack occurs, so it's somewhere in between SN1 and SN2. But the stereochemistry is inversion. So we go ahead and draw it as if it's SN2, right? Because we know with SN2 we get inversion of the chiral center here. That's what we saw, right? So it's just drawn SN2, but it's probably somewhere. Okay, either way, right, we can get an epoxide. So when it comes down to the next question, right, which is figuring out what's the starting material, what the reagents are, in terms of the reagents to make these epoxides, it doesn't matter which one you choose. Again, it's really just an advantage of scale, right? So he kind of just alternates between the two and says it doesn't matter. Right? So you want to learn them both sets of conditions epoxide. Right? And just to make it a little different than his I'll just go ahead and write something different for this one. He wrote MCQBA, but again, it doesn't matter. So really, the conditions are either or. And then the thing that to pay attention to, in case it matters, is that epoxidation is stereo-specific. So if you end up with an anti relationship here, you're going to have started with a trans alkene. So in this particular case, we've got this 8-member ring. And of course, the double bond We don't really worry about the stereochemistry. It's part of the ring. It's going to be a cis one because of the ring. So we would just draw that. But here we want to pay attention to the fact that these groups are anti. So that means that we needed a trans alkene to start with. Basically, the two ethyl groups are opposite over here, so they're going to end up opposite product. That doesn't change when we draw the epoxide product. And then here we should just pay attention to that the phenyl here was on the same side as that methyl. So if we kind of drew this in, we would just make sure to put those on the same side because they ended up on the same side. And notice he goes back and forth on how he draws the epoxide, and that's okay, right? So it could be drawn in the plane, sort of with the lines to the oxygen, just a regular line, right? A dash or a wedge. And then that means the groups have dashes or wedges. Or you just make the epoxide on a dash or a wedge, and then one of the groups is on the other, either the dash or the wedge, whichever one you didn't put the epoxide on. One of these others is in the plane. So it's two different ways of kind of showing stereochemistry. Both of them. Questions on that? So technically, this is and it's because we want the all right, we'll move on. So that was how to make an epoxide. So there's two different reaction conditions that will work for that. And now we're going to be looking at ring opening reactions of epoxide. So basically taking an epoxide, treating it with a nucleophile because the carbons attached to the oxygen of the epoxide in the ring are electrophilic. So we treat it with a nucleophile and we end up with a opening the three-membered ring. So there's a huge driving force. We call it a thermodynamic driving force for the reaction. We release the ring strain. So it's entropically very favored to open up the ring. Okay, so he talks about the sort of the rules for where the nucleophile attacks, right? So notice that it might attack right on this bottom carbon and it might attack on the top carbon, leading to two different products here. Okay? And no matter which carbon it attacks, an inversion of configuration occurred at that carbon, or the nucleophile attack, because it's attacking through an SN2 reaction. So there will be a version of configuration wherever it attacks. And typically it only matters when there's a difference, right? So for example, the substitution of the carbon is different. So we could call this one tertiary. There's 3 carbons attached to that carbon. There's 2 carbons attached to this one, secondary. There's a difference in substitution, which will help us figure out which side gets attacked. The other thing we have to look at is what are the conditions? What type of nucleophile is being used? And they're sort of broken apart into the anionic nucleophile. These tend to be typically stronger nucleophiles. Okay, so anything where the atom attack that they're doing the attacking is negatively charged. So that's an example. Bromide. Something like that, where you know you have a negative charge. So usually that involves the reagent will look something like NaOH or NaBr, right? Because that breaks apart into Na plus sodium cation, right? And either OH minus or Br minus or SH minus, right? Or something like that. So whenever you see sort of the sodium, right, being mentioned, or potassium, or usually be sodium or potassium. It could be lithium or something. Whenever there's clearly a metal involved, right, then that's an anionic condition because the nucleophile will have a negative charge because the sodium has a positive charge. So we have the anionic nucleophile versus the what we might call acidic conditions. So sometimes the anionic nucleophile might be called basic conditions, but that's not really a very good name because we're using a nucleophile, not a base, right? And they sometimes interchange those terms because typically strong nucleophiles are also strong bases. So the two nucleophile, what makes a strong nucleophile and a strong base are correlated, but they're not the same. So it's better if you think of it as sort of when you have the sodium and the counter ion. That's one type of condition. Or you might even KCl. Just to give another example there. Okay, so the acidic conditions will be different. This is when you clearly have an acidic proton that's there in addition to the nucleophile. So some examples of this might be HBr. Right? So notice that HBr, technically, it might seem like, oh, this is this condition, right? But treatment of the epoxide with sodium bromide versus hydrogen bromide are two totally different things. Okay? Because sodium bromide is sodium plus and bromine minus, whereas hydrogen bromide is an acidic proton and bromide. You have the same nucleophile, it's true, right? But this would be an example of anionic conditions, right? Where you don't have the acid there at all, basically. Versus the acidic conditions where there's an acidic proton involved. So if you see acidic conditions, that's something else. If you don't see an acid, then it's going to be the other one. That makes sense. Okay, so another condition might be, sometimes they might write later on H2SO4 and methanol. So that's clearly adding an acid, right? This provides the H+. The nucleophile is then just methanol. This entire thing is the nucleophile. And it's not a strong nucleophile. So you can use weak nucleophiles under acidic conditions, whereas you would have to use strong nucleophiles under the other conditions. Or so you could use, and if it didn't say methanol, you could assume water is there. Whether or not it says H2SO4 water or just H2SO4, you can't buy pure H2SO4. So if it doesn't mention something else, there's always water there. Right? Because the best you can do is like a 12 molar solution, which still has some water. So you can never get away with having water or methanol accompany the H2SO4. Okay, so, and we'll kind of get as we do some examples, we'll see, like, immediately we'll think about, is this acidic conditions or the other anionic nucleophile type conditions? Why does it matter, right, being able to distinguish the two of these? It matters because it's going to change where the nucleophile attacks. Okay, so you have to determine which one are we doing, right? Which one is it? That will determine which one of these is where the nucleophile attacks. Okay? And the simplified explanation is just, if you have an anionic nucleophile with no acid around, sort of strong nucleophile condition, it will attack at the less substituted carbon. Okay? So, for example, in this case, it would attack at this secondary carbon because it's less substituted than the tertiary carbon. So if it was a strong nucleophile, right, in these conditions, it's going to attack at the less substituted. If we have the acidic conditions, the nucleophile, regardless if it's weak or strong, it will attack at the more substituted carbon. And there's an exception to this. It talks about it in the book, but you won't ever get that exception. It's not in here, and it's not going to be on your quiz either. So we can just kind of keep it simple and say, strong nucleophiles attack the less substituted carbon. The acidic condition, no matter what type of nucleophile it is, the nucleophile will end up with the more substituted carbon. That's kind of bottom line. Okay, so moving on. So the first thing we want to do is look at what's the condition. So this is Na plus and SH minus. Okay, so it is the strong nucleophile, no acid involved here at all. So we then can come over here and look at the epoxide and go, okay, this is tertiary, and this carbon is primary. Okay, so then the nucleophile attacks at the primary carbon. And we'll draw out the mechanism for the first one, or just the first step at least. So we said it's going to attack at the less substituted carbon. It's an SN2 reaction. So the oxygen, okay, is the leaving group. So we break that carbon-oxygen bond to get the leaving group. And then it doesn't mention it, but there is a workup with water or an acid, and that will provide the proton for the oxygen. You can just go ahead and protonate it. So let's go here. Notice that at this carbon where we attacked, we need to do an inversion. But we don't invert the carbon that didn't get attacked. The stereochemistry there stays the same. It's a super fun of drawing another 8-membered ring. And then we're going to show inversion. So this leaving group, the oxygen here, was on a wedge. So we're going to draw the nucleophile on a dash, because we did inversion there. And then the other carbon, stereochemistry stays the same. We did not invert that carbon. So after the oxygen left with a negative charge, it picks up a proton in the workup. So that's how we draw that product. Okay, so looking at the next one, now we have the acidic conditions, right? Because we have the acidic proton and our nucleophile is chloride. So we want to pay attention to that because now we know the regiochemistry, right? The nucleophile will attack the more substituted carbon under acidic conditions. And once we kind of go through these, I'll give you an explanation of that in case it wasn't really clear in the video for the activity. Okay, so we have the, we're going to look at the epoxide, secondary versus a tertiary carbon. So it's going to attack the tertiary carbon because of acidic conditions. So we're going to end up inverting that tertiary carbon. So the mechanism is basically going to be chloride, does an SN2. I know it's a tertiary carbon, but we can do an SN2. And again, when I give you that explanation, I'll show you why. Right, the leaving group leaves, and we end up with an alcohol there. We have 6-membered ring. Pitch that in. We're going to be doing inversion, right? So the chlorine ends up opposite the leaving group. So the chlorine ends up on the wedge. And that pushes the methyl back. So there's that inversion of that stereocenter. And then this one, the other one does not get attacked. Carbon does not invert. That would be the product here. Stop me if you're lost. Keep going. So we have the next one is we're looking at the reagents. We've got the K plus and I minus. No acid, which means the nucleophile attacks the less substituted carbon. So it's tertiary versus secondary. Secondary is the less substituted. Iodide will attack there. So we draw out the product. It likes rings. Maybe we're going to go into the next page and have rings. Anywho, we have inversion here. So this was on a wedge. So the iodine will be on a dash. And then the other carbon change. The methyl is still down and the OH. Okay, next one has the acidic conditions, right? And then this is our nucleophile. Nucleophile acid. So nucleophile will end up having more substituted carbon, except for when we come over here and look, we see it's the same. Okay, there's a plane of symmetry here. So it doesn't really matter which carbon gets attacked in this case. You could do either. Same thing. So we'll just kind of sketch that out. We get to your 7-member ring. Kind of start there, go out. Okay, and let's say I chose my methanol to attack at the top, and it doesn't matter. Right? What I'm going to make sure to do though is inversion. We'll end up with, I just basically decided it would attack here instead of the other one, but it doesn't matter. The important thing is that where it does attack, it undergoes inversion. And then, and after the nucleophilic attack, there would be a proton here, and it would be a positively charged oxygen. That just gets deprotonated in the workup. So you're worried about that.
I have a question. Why
Yes.
is the OH going backwards?
Because this carbon here has the OH, the oxygen pointing back, and nothing attacked there. So we don't do anything to that stereochemistry. It stays the same. So basically, this carbon with the down oxygen and a proton come with that. That makes sense. Okay, so, and it will kind of, when we review the mechanism right after this, I'll show you the full mechanism, what's exactly going on. A similar example. But we're just trying to draw the product. Okay. Yes.
For that one, would there be an enantiomer as well because it could attack on either carbon?
Yes.
Because they're
yeah,
both,
so
okay.
it could technically, so it could have attacked here, right? And then you would get, so let's think about that, right? So let's draw the other one. So if it had attacked here, you would have the methoxy there, OH there. So those are enantiomers, basically, because if you just flip this over, this would be back, this would be up, so mirror image. Right? So yes, we get the enantiomer. Good question. Other questions? Okay. So this is LAH. Remember, LAH basically provides the equivalent of a hydride. Really, it's going to be from the LAH structure. But when you think about this, there's no acid around, right? So this is the strong nucleophile condition. And that means it's going to attack the less substituted carbon. This is secondary, and the other side is tertiary. So it will attack the secondary carbon. But we're just adding a hydrogen. So when we draw that, we don't even necessarily draw it in. So basically we've added a hydrogen here and we've lost the oxygen. So this carbon just becomes a CH2, which is nothing to write about. And then we have no change in terms of stereochemistry of carbon. Everybody okay? So from this, the takeaway is being able to determine, right, is it acidic conditions or not? That's going to change the regioselectivity. So that's important to be able to note. Right? And then the nucleophile, where does it attack based on that? Okay, I'm going to get into some little more explanation because I know some of you are probably wondering
Question.
why the regioselectivity is the way it is, and I don't watch the videos to know what he says about it or not.
It's Dr. Gilly.
Yes.
Good question. Sorry, my video cut out there when you were talking about LAH and whether that's acidic or not.
Okay. Yep. So that is not acidic. Because basically, think of it as like a hydride donor. Okay, so it's like BH with 2 electrons minus. So it is the strong nucleophile condition, not acidic.
Okay.
And a Grignard reagent also would be the same thing, not acidic. Grignards are very, very basic. Okay, so let's go into a little more explanation. For example, we could do this. When you use a strong nucleophile, for example, like LH, but any strong nucleophile, basically not acidic condition. Because we're doing an SN2 reaction, there's going to be a natural inherent preference for the less substituted carbon. Because we know SN2 reactions, they require the nucleophile to approach from the back. Right? It's a sterically hindered situation, and so it's better if the carbon is not as severely sterically hindered. So those sort of conditions will always go basically for the less crowded carbon. Because it's a typical SN2 reaction with a strong nucleophile. So it's sort of the SN2 that you most know and are familiar with. But let's see how this changes under acidic conditions. We can go ahead and use this. So we've taken this, and now, for example, we are treating it with HBr. So because we're treating this with an acid, acids have a strong motivation to get rid of their protons. So we can protonate the oxygen of an epoxide. So now we don't really have a strong nucleophile yet. Right? We don't really have one until the proton is transferred. Then we get bromide. We don't have it initially. So now we have protonated epoxide. So now we've got this, and we also have that proton transfer step. So here's the thing, right? An oxygen, you guys know oxygen's electronegative. It doesn't really like to be positively charged all that much. It's very reactive. And this carbon, right, is tertiary. One thing we know about tertiary carbons is that they, when they have a carbocation, for example, they're relatively stable. The tertiary carbocations are pretty stable. So what happens is this bond between the carbon and oxygen, specifically to the tertiary carbon, starts elongating. Okay, so it is not as strong a bond as drawing this wedge here would imply. Right? So we can kind of think of it as it's still up, right? But it's sort of elongated. Hold on a second. Receiving some requests from mom from outside. Cameron, what's up? Honey, I'm making a video right now. So unless it's an emergency, ask the babysitter. Okay. So we have, this is sort of, they're both still on a wedge. And I'm just drawing this bond as sort of elongated. So what that does is it splits the charge, or it shares the charge. Instead of being completely on the oxygen, now only partially on the oxygen, because it's taking those electrons from the bond and really grabbing them and taking them towards the oxygen. So that means that the other carbon is sharing part of the positive charge. And then there's a methyl going back first. So basically, when you have a tertiary carbon specifically, the bond to the oxygen elongates, but only when the oxygen is present. That occurs. So there's not a true carbocation here, but there's like a partial carbocation. Okay? And that helps because the oxygen has more electron density, so it's happier, right, with a partial positive than a full positive. And the carbon is able to take some of that positive charge, but only because it's a tertiary carbon. So what happens is this is the leaving group. It's already kind of almost left, right? Think about this. Essentially, we've taken the electrons and mostly given them to the oxygen. The leaving group has already kind of started its pathway to leaving that carbon. So this carbon, right, is not truly sp3 anymore. And it's not as sterically hindered as you would think. Okay? It's not even really tertiary anymore. Think of it as if it was sp3, there would be a tetrahedron. This group has already started to leave. So one of the groups in the tetrahedron has already started to go. What happens to the other groups when that happens? Right? So we have a little tetrahedron. As the leaving group leaves, then what's going to happen to these? The angle still going to be 109? No, right? As that leaves, it starts to get more into the best angle it possibly can, which is 120. So they want to get further away from each other. So it starts to, the umbrella starts to open up, so to speak, right? And we end up, the groups further apart. What does that mean? That means there's more room for backside attack. So if a nucleophile needs to come in, it doesn't have to compete with these groups, right, that are really close together anymore, because they've already started to open up to a planar situation. There's much more room for a nucleophile to attack from the back at this point. Once this has already started to leave, this becomes more trigonal planar, not as sterically hindered. The nucleophile can attack from the back. It won't attack from the front because it's not completely gone. It's just started to leave, right? So if it was completely gone, you get a carbocation here, the nucleophile could attack from the top. But it's not completely gone. The top is blocked still, some of the bond. It always attacks from the back. So that's why we get a nucleophile attacking from the back here. And we still get inversion because oxygen is blocking the top, so the nucleophile has to come in. We still get inversion, but we get attack at the more substituted carbon in an SN2 reaction. That's a little bit weird, but it can happen in some cases. So we would get the inversion. So the leaving group was from the top, right? So that means the nucleophile has to be signed. That pushes this methyl group here up. We do that inversion, right? And then we end up with the OH on the side. That's the product. So it's still SN2, but some people start to call it SN2-like. Why is it SN2-like? It's SN2-like because you get inversion. But it's not SN2 from the standpoint of we attacked the less substituted carbon. We actually attacked a tertiary carbon, which is not very SN2. So it's kind of somewhere between SN2 and SN1. Right? We kind of, in the first semester course, we teach you like they're separate things. So either do SN2 or you do SN1 and they're separate, right? That's just an oversimplification. there is such a thing as somewhere in between. We just don't want to teach you that because it's too confusing at first. Okay. So anyway, that's what's happening in the acidic conditions. The bottom line is we need to know that the nucleophile, regardless of where it attacks, it does an inversion, but it will attack at a tertiary carbon under acidic conditions. Okay. Otherwise, stronger nucleophiles go for the less substituted carbon. Why is that? Because it's less sterically hindered at this carbon and none of these bonds have weakened. Okay, so it's still a sterically crowded situation for that nucleophile. Does that make sense? Any questions on that? Okay. So we're going to move into some acyclic. I thought. Weird how they're all rings. There must be another place non-ring. Which if I had looked at this a little more closely, I would know. I don't really have to prepare anymore. The gift of having taught this for years. Okay, so here we go. We're going to do epoxide ring opening reactions of non-cyclic backbone. Okay, so notice, right, he has a nucleophile. It is anionic. We have a strong nucleophile, no acid. So it's going to attack the less substituted carbon. I've shown that attacking the secondary carbon because it's a non-acidic condition. Okay, so but the weird thing about the way it's drawn, it's easier to see this carbon, which has not been attacked, and the stereochemistry is clearly not changed. Right? So there's no inversion there. This one is a little bit strange, but I promise you it's been inverted. Right? It's the reason why the wedge is still a wedge, right, is because the group that's switched is in the plane, which is just kind of the virtue of where. So the leaving group is in the plane, and the bromine has attacked from the back in the plane, right? And then the leaving group leaves. So we draw the bromine having come in from the back where the leaving group used to be. And when we do that, we're able to keep the group on a wedge, still on a wedge. And we've done inversion. I don't know if that, you can kind of follow that. Right? But basically, if you were to figure out if this is R or S, it will have inverted to the other, okay, by drawing it this way. So that's kind of the way we want to draw it. Okay, so let's do some practice problems. What that looks like. So we have KBR. So the first thing, of course, we're going to look is we are not under acidic conditions. We still need to know about that. So that means that we're going to attack the less substituted, which is going to be this carbon. So less substituted on the other side. So we'll have the bromide attack here. And again, you don't have to draw the mechanism out like I'm drawing. Right? I'm just drawing the first step in the little bit. It's just showing it to you for clarity, but you just draw the product and that's fine. So then the leaving group leaves. So when we draw that, we want to make sure to include, so the question is, are there going to be any stereocenters in the product, right? This bromine is attacking this carbon and there's 2 hydrogens here, so that's not going to be a stereocenter. Over here, right now it is. We have 4 different groups, right? We have the ethyl, the methyl, and the 2 different paths. But once we have this, the question is it still going to be a stereocenter? The answer is yes, because once we add a bromine here, this will be a different group. This will be ethyl, this will be methyl, and that will be an OH. We will still have a stereocenter, so we want to make sure that stereochemical information. Or you could kind of, sketch it out and then realize, oh, it's not a stereocenter, and just not having the gaseous. Okay, So we'll go ahead and draw this, right? And then we've got this carbon from. Again, this is not a chiral center. Dashes and ridges, that carbon. Okay? And the oxygen, or sorry, the hydrogen here on the oxygen comes from the workup that he isn't including, but is always occurring in reactions. Okay, the next one is this deuterated lithium aluminum hydride. Right? So basically think of it as, instead of hydrogens, we have deuteriums. Talked a lot about deuterium before, just an isotope of hydrogen. This is again a strong nucleophile, not acidic conditions. So we're going to attack the left substitute. And there'll be lots of leaving group there. So when we draw this out, so this have the methyl here. So this carbon just got a, well, it got a deuterium. Go ahead and add instead of a hydrogen. And then we have the OH. And there's a hydrogen pointing back here, which wasn't drawn in, so I'm not going to draw it in. Makes sense? Okay.
Does it matter if you draw the deuterium pointing up or down on that?
Not in this case. Not in this case because there's no stereocenter here. So it doesn't matter. When there is a stereocenter here, it will be important to draw it kind of like I did with the film. Unless you know, rotate it, which is also. So what basically right now it doesn't matter. We'll talk about it more when it doesn't. The reason is it doesn't matter because there's no stereocenter. So it's just basically a bond rotation. There it is. Okay, so next we have the acidic conditions, right? So here we have the acid, and then the methanol, the oxygen of the methanol will be our nucleophile. So with the acid, first we get protonation of the epoxide in the first step. Okay? And then methanol attacks, and it will definitely attack this carbon because it's the most substituted. So that's where we want to go under acidic conditions. We're going to do nucleophilic attack. Right? Doesn't really matter if you kind of come in from here or the other. You're going to do inversion there. As long as you know that, then you're good to go. Loss of aluminum. Okay, so when we draw this one, we're just going to be careful, right, not to change the way this one is drawn. And because he went ahead and drew the hydrogen pointed back, I went ahead and did it. That's optional. And we have our bond there, right? Now here's the thing when you do it this way, right, is because the epoxide is in the plane and we're showing the methanol coming from the back, we can keep these groups on the same dash or wedge that they were before and show the nucleophile sort of opposite of where the leaving group left. And then that will be inversion. So we'll end up with OCH3. So is that okay? Does that make sense? So in this case, if you want to keep the wedge and the dash, right, as they are, then it's important to draw the nucleophile up down here. If you had drawn it up here, you would need to switch these. Essentially, you're flipping it over. It's easiest if you just kind of follow that. Okay, so next one, we have a Grignard reagent. So a Grignard reagent is the strong nucleophile category, no acid. going to attack the less substituted carbon. And now we're getting a methyl there. So in terms of draw stereochemistry, we can keep this one as is. And then we have add that extra methyl. So now we notice, because we went ahead and drew it, right? Notice, oh, this carbon is actually not a chiral center, because there's two ethyl groups now. Not a chiral. So we didn't actually have to draw any stereochemistry. We could have just, this is essentially equivalent to just drawing it this way. No need for dashes and wedges when there's no stereos. Moving on to the next one. Now we have sodium hydroxide. So this is Na plus and OH minus. Okay. And so that's a strong nucleophile, no acid. So it's again going to go for the less substituted carbon. Okay. And we're going to make sure to show stereochemistry. We're just going to keep this as is, exactly like it's drawn, and then this becomes, and again, it doesn't matter sort of what angle this is, because this is not a, but this is definitely a chiral center, so we want to make sure that. Okay, last one is acidic conditions. Right? We've got H plus and Br minus. So it is the acidic condition, so we are going to protonate the epoxide, right? And in that case, the nucleophile adds from the more substituted position. So it's going to go for side with the phenyl. And that means that we have OH on that carbon. And we've done an inversion here. So just draw bromine coming from the back. And keep the phenyl on a wedge. As long as the nucleophile is pointing opposite of the leaving group, then we will draw an inversion. Questions on that page? So you will probably want to practice that on your own. Make sure you draw the same thing that I'm drawing for the most part. That can be confusing. One thing to watch me do it looks easy when I do it. It's another thing to draw it yourself. Okay, or recognize it. All right, so fill in the empty boxes with the proper structure or reagents. We have an epoxide here. It looks like we're adding in this nucleophile. And it did attack at the less substituted carbon. It's probably going to be a strong nucleophile. So because we've made this new carbon-carbon bond, we used a Grignard reagent. So the Grignard reagent would be just whatever you see getting added there. In this case, it's called a vinyl. And you can mention or not mention. I tend to mention the acidic workup, right? But he tends not to, so optional, I guess. Next one, we are adding LH. Remember that that's going to deliver a hydride at the less substitute. And that's just going to make a CH2 here, so we're not really going to do that carbon. But the other carbon, and I just realized after I drew that out that, oops, this is actually not a chiral center. So it would be okay to not include any dashes or wedges. For the next one, I actually think this one is the trickiest one, right? Because it can be kind of hard to see. But basically, it looks like we probably started from an epoxide, since, you know, you might note that they're all epoxides here as the reactant. We need some sort of epoxide. We're going to be treating that with acidic conditions, water as the nucleophile, right? And that we need to pay attention to some stereochemistry here. So make sure that whatever epoxide we have is consistent with the stereochemistry that we see in the product. So if we draw the epoxide in the plane, start there, then we just have to see, okay, what's attached. So we can have a methyl here. Let's say this carbon did not undergo inversion. Then methyl coming out this way would end up over here with the nucleophile attacking on the back. So it's sort of reverse engineering the stereochemistry of the epoxide, which is probably the most challenging thing to do. Okay, and here we have to look at, okay, what did we do, right? So there was an epoxide. This CH2 group became a methyl. So we added a hydrogen. The way to add a hydrogen is to use LH. Essentially, think of this as this is CH2, right? It became CH3. We added hydride. And then this one is also a little bit tricky, right? So once we add the base, sodium hydride base, it's going to deprotonate the alcohol. So initially we get the alkoxide. Then it's clearly going to do an intramolecular reaction. There's always a few challenge ones. Okay, so from here, we have to think about, okay, basically here's our epoxide, which is these two carbons are electrophilic. Here's our nucleophile. What do we note about the nucleophile? It's anionic, it's a strong nucleophile. There's no mention, right, of acid in this reaction, no acid. So it's definitely going to go for the less substituted carbon. So it can basically, all of these bonds have free rotation. It can rotate around to reach the back. And so we'll basically rotate all the way around to reach the back of the less substituted carbon to do the loss of ozone. So this is where it gets tricky, and I recommend sort of numbering things so that you can see, you know, where are you making your new bond, where is everything numbered, right? It'd be really helpful. And it doesn't have to be a carbon to get a number. Right? So for example, the oxygen is going to be part of the ring. So I'm just going to call my oxygen atom number 1. Then I can keep going, 5, 6. And so I'm making a 6-member ring where one of the atoms is an oxygen. So for example, I could draw a 6-membered ring. One of the atoms is an oxygen. Where that was off. And then I can start numbering, right? My ring. So this is number 1. I can go around this way. So we can kind of see, okay, I made a 6-membered ring. Look how number 1 oxygen is now bonded to number 6 carbon. Right? So we made that process. So let's see. A carbon number 2 is a CH2 group. Okay, there's nothing else attached there, so good. CH3, CH2 group. Okay, carbon number 4 is a CH2 group, so nothing else attached there. Carbon number 5 has got some stuff attached, right? It has a methyl, and it's going to have an OH. So it's going to have a methyl and an OH. And right now, I'm not going to worry about stereochemistry, and then I'll go and figure it out later. So for now, I'm just going to put methyl. I know that's what's going to be attached here, carbon number 5. And then carbon number 6, we lost the leaving group there. So it just has the oxygen intact now. So this is the basic structure, but we don't include stereochemistry yet. Clearly, this is a stereocenter. It's still a stereocenter. So we have to figure out the stereochemistry. One thing to note is that it was not attacked, right? So this stereocenter did not invert. Did not invert. So whatever it is, if it's S, it should remain S. If it's R, it should remain R. Right? So we're going to figure that out. So in terms of priorities, oxygen is the first priority group. Right? And then we have this CH2 that's also attached to the oxygen is the second priority group. Right? And then the third priority group is this group here. Methyl is the fourth priority group, and it's pointing out at us. So no matter what we get, we have to the priority group is out at us. Right now it looks like R because it's clockwise, but we have to switch. Which means that whatever I have up here should still be this. And I've drawn it differently, so it's weird, but I just have to figure out what would it take for this to be S. Okay, so this should be our first priority group, second priority group, third priority group, right? So this looks like clockwise. And it would be R if our fourth priority group is back. So I'm going to go ahead and make our fourth priority group out at us so that it becomes S. So that's what it takes to get this to be S. And it should not have been inverted because it wasn't the carbon. So sometimes it takes a little extra work to figure out. And it definitely did in that case. Challenge question. So instead of redrawing, just a little start. Moving on to the synthesis, we have something similar that we've seen before, right? We know we can, starting from an alkene, we have only one choice. We have to do a radical halogenation. So then bromine will end up on the more substituted carbon. I need to introduce a group of that carbon. So I probably need to get a double bond here so that I can introduce a group of that carbon. So then I'm going to need to do elimination. We've actually seen this before. Now my carbon is a double bond. If I'm going to add in an alkyne to get this alkyne, so if I'm going to do use an alkanite ion, then I need a leaving group attached to that carbon. So that means I need to, for example, a leaving group would be bromine. I want that to add less substituted carbon, so we need the anti-Markov addition of HBr, so that I can end up with my leaving group here. Now I can add the alkanite ion. Get me to this A, first product here. This is A. Now it looks like I need to reduce the triple bond to a trans alkene. So we have to remember the conditions to do that. If you want to reduce a triple bond to a trans alkene, then you need sodium metal. That would be a chapter 9 reaction. And so this is now B. And now we need to form the epoxide. Remember, it doesn't matter if you do MCPBA or bromine and water followed by sodium hydroxide. They do the same thing. So a little bit less work to write MCPBA than the other, so we just write that. Doesn't matter. And that would form the epoxide. And notice how these groups are opposite, trans, and then they'll be opposite. These are trans. And I can even write or the other condition. Either one of those. Is that okay? Is okay with that? Moving on then to this one. By the way, I noticed his key on this one isn't right. He does make this product, but he doesn't ever make this right on the key. If you look at the key. So don't be surprised if what I draw doesn't match the key. It's just because he didn't draw the key. So we have, again, starting with an alkene. Cyclohexane, we only have one. Have to do radical halogenation. We're going to end up with a bromine. And then now we need to think about, okay, how can we make this carbon-carbon bond? Because we are clearly adding these two carbons, right? Add two carbons. So, and we need to make a new carbon-carbon bond. So we have two choices with that. We can either do an alkyne or we can do a Grignard. And in this case, I think it makes more sense to do it. We already have the alkyl halide here. Right? So we can make a Grignard directly from this to make that new carbon-carbon bond. So this can, you can add magnesium. We don't isolate the Grignard, so that's the reason why oftentimes if I draw it, I'll put it in parentheses. Sorry, I actually want to draw a Grignard. And then now we can make that new carbon-carbon bond. And what do we want to do? We need to add two carbons. And we need to make sure whatever electrophile we end up adding here has to have two carbons. So let's say best one here. So what if we, and there'll be some sort of acidic, which is sometimes not mentioned, sometimes just written at the bottom. Okay, so what would we get from that? We would add our two carbons and we would end up with alcohol. We do that. Which is good, right? And then now we need to just figure out how to get rid of that and get an alkene. So having an alkene here is the Zaitsev product. The goal is to get this, which you can label as. Notice I put the methyl sort of pointed up here and not down here. That doesn't matter. Because you just scoop it over. So anyway, the important thing is that we're getting the most substituted alkene, right? The double bond is forming here, and not. So with the Zaitsev product and an alcohol, easiest to just do H2SO4 and heat. Alternatively, you could also tosylate with TSCl impurity and then treat it with a small base like sodium hydroxide. So alternate conditions, a little bit longer. That's a disagreement. But you could tosylate and then you could treat it with a small, strong base to GAE2 reaction to get there. There's options. And then from here to the product, we only actually need one step. We just need to do our Markovnikov hydration. If there's going to be no rearrangement, so might as well just do H3. Okay, everybody. Right. I think that's the end of today's activity.
Excuse me, I have a question.
Okay.
For 4, the last one with NaH as the base, so we're assuming that there's water as well too, right? To protonate the...
No.
No?
Oh, you mean for the workup? Yes.
Yes.
Yes. At the end, there will be a workup.
Okay.
Yep, that provides this hydrogen. Yes.
Okay, thank you.
Yeah, so for whatever reason, he doesn't usually mention the workup in the conditions, but it's always there. You can't ever end something that is charged.
Yeah, because the textbook, it shows water, so it's
Yeah.
a little confusing now, you
That's
know.
just, yeah, it's that workup at the end. But
Okay.
basically, when I said no initially, it's because you don't use sodium hydride with water present. So it has to be completely anhydrous initially.
Okay.
The solvent is rigorously purified of any water. All the glassware is purified. And then only after it's done what it wants, then you add the water in at the end.
Yeah, it makes sense because it's shown as a second step in the book anyway, so.
Yeah, so the book usually includes the workup. And unfortunately, Dr. Wynn doesn't. And so it's a little bit hard I want to match his style as much as possible so it's not confusing. Sorry. But it can be a little bit. I usually go for more detail than less detail, but for that reason, that also can be confusing for some students and lead to less success. So it's kind of a toss-up.
I like the more detail just because I won't forget, or I don't know.
Good
I like
students usually do. Yeah. So they usually do, but then that's why I'm, like, it's really good if you like a lot of detail to take me because I provide a lot of detail. But and unfortunately, I can leave a lot of students who are weaker content behind.
I don't understand the last step with how the H3O changes to the final product.
Okay, back over here. So this is a Markovnikov hydration. We're basically just doing this double bond, right? And we're adding H and OH across the double bond. And so this is a hydration. It's a chapter 8 reaction. And it's going Markovnikov because the OH ends up on the more substituted carbon. We call it Markovnikov hydration. So it's basically, it's the same exact thing as, for example, something you probably have seen before, something like this. We're adding OH and H across the double bond, so we call it a hydration. And the OH gets on the more substituted carbon, so it's a Markovnikov hydration. So it's the same thing on a more complicated molecule.
Where does the other methyl come from?
Yeah, that's what I'm not getting either. Exactly.
Oh no, I missed that methyl. You guys are paying attention. I just didn't see it. Okay. We're gonna have to change the that methyl. So once we get to the alkene, so our goal here is which is very different than what I initially thought. Okay, so in order to do this, we need to do a Grignard. Okay? If we're adding a carbon-carbon bond, okay, so this is a new carbon-carbon bond, adding that carbon, right? So we're gonna target some sort of Grignard in order to do it. So the easiest thing to do actually in this case is to use an epoxide. So if we convert this first to an epoxide, and then do we need to worry about stereochemistry here? Not really, because this is not a chiral center. This one eventually is going to not be a chiral center, but you could draw it in, right? So if you wanted to, you could kind of keep this consistent. To starting from the south. Again, if we're making epoxide, either condition. Okay? And then now we can actually treat this with a Grignard, so a methyl magnesium bromide, followed by an acidic workup. And so what's going to happen is the Grignard, remember, is a strong nucleophile and no acid. Right? So we can go ahead and have it attack a substituted carbon. So after it does that attack, just the alkoxide and then and then we just need the acidic workup to get to the product. So this is better answer to the end. So again, if you didn't include any stereochemistry here, it wouldn't really matter because the starting material and the product don't have stereochemistry. You don't really have to carefully consider it. Look more closely.